All right, so here's the 3-5 lecture for talking about the derivatives of trigonometric functions. We're going to start with a simple question. What do we think the derivative of the sine curve is? Well, to start exploring that question, we might start by saying, well, what does the sine curve look like? Kind of like this. Goes on that way too. Yeah. All right. And when we are interested in talking about the derivative of the sine curve, we might say, well, what are some important points of interest? For example, here is where there's a horizontal tangent. Here where the angle is pi over 2. And by the way, we're going to do all of our angles in radians. So pi over 2, this is pi, 3 pi over 2, 2 pi, right? And so we might say that the original function f is here, and f prime, we know that at pi over 2, it's going to have the value 0. All right? And then maybe we look over here and say, well, 3 pi over 2, at 3 pi over 2, we have another 0. Oh, and in between there's a bunch of, it's decreasing, there's negative slopes. So in between here, there is negative slopes, so the derivative curve will be negative. Where'd f double prime there? That should be f prime, right? And then we have increasing slopes here, and so we have an increasing function there. We have increasing function there, so we're positive there, and we might notice that indeed what we get is something that looks like the sine curve. So if the original function is sine of x, then the derivative function is cosine of x. Now, this is not a rigorous proof that this is true, and there is this QR code over here that you can scan, and I'll take you to some videos that do a much better job of describing with a lot of rigor using our definition of derivative why this is true. But this is a nice little graphical representation, and it's something that you can lean back on when you're trying to remember what the derivative of sine is. What if we did this again? What if we did this again? What if we said we've got an original curve, which is the cosine curve? All right. And, oh, okay, what do we know about this cosine curve? It has a horizontal tangent. It has a horizontal tangent at 0. So the derivative, if this is the original function, and this is the derivative function, at x equals 0, the derivative function is 0. And it looks like over here, there's another one. And let's just do a quick thing. This is pi over 2. This is pi. This is 3 pi over 2. And then up here where it gets high again there, it's 2 pi. All right. So we have at pi over 2 something going on, but at pi, we're definitely back to 0. It looks like there's a horizontal tangent again at 2 pi. Right? Now, in between 0 and pi, this function is decreasing. And between pi and 2 pi, it's increasing. It has all those positive slopes. And you can see that this curve looks a lot like the negative sine curve. It looks like the sine curve, except it's been flipped over the x-axis. So I am going to ask you to memorize those two facts. The derivative of sine is equal to cosine, and the derivative of cosine is equal to sine. All right, let's take a look at where we might use these facts. Find the derivative of this expression. Find the derivative of this expression, which we will write as a quotient. So we must have to apply the quotient rule. So I break out my mantra, and I get bottom times the derivative of the top. And I guess I'll write that down as the derivative of sine minus the top times the derivative of the bottom and that's all over the bottom squared. Now, what is the derivative of sine? Well, we just learned about that. That's cosine. And what is the derivative of cosine minus 2? Well, derivative of cosine, as we said, was negative sine. And the derivative of negative 2, well, that's a constant. So that is just going to go away. And that leaves me cosine x minus 2 quantity squared. Now, I would say in a normal situation, we'd be done there. But something nice is going to happen if we try to clean this up. Let's expand those first two terms, cosine squared minus 2 cosine. And then I got a minus sign and another minus sign, which nets out to a plus sign of sine squared. And then this is all over cosine of x minus 2 squared. Now, the reason why this is interesting is because we have a cosine squared and a plus sine squared, and we recognize that as a Pythagorean identity. We recognize that the cosine squared plus the sine squared is equal to 1. So this becomes 1 minus 2 cosine x all divided by cosine x minus 2 squared. And there's our final answer. That's the one that's more likely to show up as your multiple choice answer. In the next example, we'll apply this to velocity problems. We're told that the position function is given as 3 sine t. What is the velocity? Well, the derivative of position with respect to time is velocity, which means the derivative with respect to t of sine of 3t is 3 times the derivative of sine, which is cosine. And then what about acceleration? Well, the acceleration is the derivative of velocity. So it's the derivative with respect to t of 3 cosine t, which ends up being 3 times negative sine of t, or negative 3 sine t. And there's our two answers. Now, some people may have been asking, by the way, what if we took the derivative of acceleration? Then we get another thing, and that's called jerk. So just letting you know that it goes on after jerk as well, but we're not going to talk about those things. Could we find the jerk of the example? The jerk is the derivative with respect to time of acceleration. The derivative with respect to time of negative 3 sine t in this case. Set aside the negative 3, take the derivative of sine, and you get cosine. And again, you're going to need to memorize the derivatives of those trigonometric functions. Let's go on to the next page. Now, what we have are the two facts that we just talked about. Derivative of sine is cosine. The derivative of cosine is negative sine. But the derivatives for all the other trigonometric functions also exist, but we can derive them based on the fact that we know sine and cosine. Let's do an example. So choose any of the four. We're going to choose tangent. All right. The derivative with respect to x of tangent, which I'm going to rewrite based on the definition of tangent, and that is, I'm going to write that this is sine over cosine. And now that I've written tangent in terms of sines over cosine, I can use the fact that I know what the derivative of sine is, I know what the derivative of tangent of cosine is, and I know the quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom, which is negative sine. We should put that in parentheses. And this is all over the bottom squared. again, although on a quiz I wouldn't make you do this, if we do those simplifications, we will note that we get another Pythagorean identity, and we get 1 over cosine squared, which does not match this answer, except if we remember that secant is 1 over cosine, so this is actually equal to secant squared. So we can derive any of these. I think some of them are exercises for your homework. Here's another reason why I have this table written as it is, and that is, I want you to note something. I've got derivative of sine is cosine. Derivative of cosine is negative sine. But let me say this with a little different emphasis. The derivative of cosine is negative sine. Or the derivative of cotangent is negative cosecant. Or the derivative of cosecant is negative cosecant cotangent. So here's something to help you with your memorization tasks. The derivative of something that begins with a co ends up having a negative. Okay, one little thing. Another thing that you might stick away is that what I'm seeing here is that there's one tangent, but there's two secants. Down here, here's a secant, here's a secant, here's a tangent. There's one tangent and two secants. So if that's helpful, one cotangent, two cosecants, here's a cosecant, here's a cosecant, and a cotangent, one cotangent and two cosecants. If that's helpful to help you memorize it, great. And if it's not helpful, then forget about it. Do some other trick in order to memorize the derivatives. All right, we got a couple more examples. Find the lines that are tangent and normal to this graph at that point. Okay, if I want to find a tangent line, what do I need? I need a point, and I need a slope. For the point, it looks like I have half a point, which is 2. All right. For the other half of the point, how about I plug in 2 for x? I get tangent of 2 over 2. And I don't know what that is off the top of my head, but I'm just going to write it that way and say, that's some number. Okay, what about the slope? Well, what is f prime of x? Well, looks like we got another example of a quotient rule. So I've got the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1. And this is all over x squared. So x times secant x squared minus tangent x all over x squared. And of course, for my slope, I'm going to need to know what is that derivative at? 2. So it looks like I've got 2 secant squared of 2 minus tan of 2. And this is all divided by 4. Okay, big long mess. 2 secant squared of 2 minus tan of 2 all over 4. And if I want to do the tangent line, then it'll be y equals tangent of 2 over 2 plus 2 secant squared of 2 minus tangent of 2 all over 4 times x minus 2. Okay. All right. The normal line is going to be found by simply taking the negative reciprocal of that slope. So let me change the sign. Let me create the reciprocal of, not x, that'd be 2 of that, and then multiply that by x minus 2. And there's your normal. All right, last example for this recording. What is the second derivative of y if y is secant of x? So let's take the derivative of both sides of that equation. And I get y single prime. And of course, from that table above, we remember, and you're beginning to memorize, the derivative of secant is secant times tangent. All right. What about the derivative of the first derivative? Well, y double prime on that side. That looks like a product rule. So let's declare this to be first times the derivative of the second plus the second times the derivative of the first. See how I say that every single time I apply one of these rules. So it's secant x times derivative of tangent, which is secant squared of x, plus tangent of x multiplied by the derivative of secant, which is secant times tangent. And if we clean that up, we get secant cubed plus secant x times tangent squared. Now you have enough to do your homework, and I will see you later. Bye.